Alright, so in this video I'm gonna be explaining another paradigm, another approach for domain adaptation, because so far you have seen two different extreme approaches for domain adaptation. The first approach, which is a shared encoder, everything is shared, but the second approach that was the topic of the last video was we had two different streams, source and stream, and we had some sharing in between for different layers that they have, sharing different layers, just like continual learning, that we want the parameters to be very close to each other. We want the parameters of source and target networks in their respective streams to be close together. But today it's in the combination of the first approach and the second approach. So unlike the second approach, which is shared, of course it is sharing among layers, but it also has a encoder. So it's a combination of approach 1 and approach 2. So it's a combination of them, and you will see this interesting, and I can say it's an evolution of the approaches that you have seen so far. So this important article in 2016, very important, there was a motivation for this paper. The cost of large-scale data collection and annotation often makes the application of machine learning algorithms to new tasks or datasets prohibitively expensive. One approach circumventing this cost is training models on synthetic data where annotations are provided automatically. Despite their appeal, such models often fail to generalize from synthetic to real images, necessitating the domain adaptation algorithm to manipulate these models before they can be successfully applied. Existing approaches focus either on mapping representations from one domain to the other, or on learning to extract features that are invariant to the domain from which they were extracted. However, by focusing only on creating a mapping or shared representation between the two domains, they ignore the individual characteristics of each domain. We suggest that explicitly modeling what is unique to each domain can improve a model's ability to extract domain invariant features. Inspired by work of private shared, as I said, it's a combination of these two approaches, the shared one and the private. So it's an evolution of these two approaches, and it's a kind of mixture of them. We explicitly learn to extract image representations that are partitioned into two subspaces, one component which is private to each domain and one which is shared across domains. Our model is trained not only to perform the task we care about a source domain, but also to use the partitioned representation to construct the images from both domains. So you see the private target encoder, you see the private source encoder, so both of them are private. But you have a shared encoder that shares between source and target, so all of them are. So that is the shared similarity loss. And we have two private, so in total we have three different losses, and then we have a reconstruction loss. Because you can have a shared decoder, we have a shared encoder, but we cannot have a shared decoder. So they drew inspiration from that. And finally, classification loss that everybody is familiar with. So X represent labels of number of S samples, source samples, number of target samples, and E be a function parameterized by theta c, which maps an image X to a hidden representation, representing features that are common or shared across domains. And this E of P, E of private, so E of this private, E of P to each domain, that are private to each domain. And D is just decoding function mapping hidden representation to an image reconstruction. And G is just a specific task-specific function. So we are learning that we have a combination of losses, task, reconstruction, the difference, and the similarity. So these hyperparameters, alpha, beta, gamma, control to what extent you care about each of these different concerns. And we want to minimize negative likelihood of the ground truth class for each source label. But we use a scale invariant mean squared error term for reconstruction. The difference loss is also applied to both domains and encourages the shared and private encoders to encode different aspects of the inputs. We define loss via a soft subspace orthogonality constraint between the private and shared representation of each domain. And H sub C, sub S and sub T, are matrices whose rows are the hidden shared representations. And these H sub C, H sub T, and H sub S from samples of source and target data. Similarly, these matrices, those whose rows are the private representations. So these are private representation of source and target. And finally, the difference loss encourages orthogonality between the shared and the private representation. And this is Frobenius norm. So the similarity loss encourages the hidden representation from the shared encoder to be as similar as possible, irrespective of the domain. And then we have similarity losses. Maximizing such confusion is achieved by gradient reversal layer that I've explained in a different video, and a domain classifier trained to predict the domain producing the hidden representation. So formally, for some function f, this gradient reversal layer is defined by Q with this gradient. And the domain classifier Z here is just domain classifier. Parameterized by theta Z, maps a shared representation vector to a prediction of the label D hat. So learning with this gradient reversal layer is adversarial in that theta sub Z is optimized to increase Z's ability to discriminate between encoding of images from the source or target domains, while the reversal of the gradient results in the model parameters learning representations from which domain classification accuracy is reduced. Essentially, we maximize the binomial cross entropy for domain prediction task with respect to theta sub Z, while minimizing it with respect to theta sub C. So D sub I is just the ground truth domain label for sample I. And they use, because we are working on domain adaptation, they use maximum mean discrepancy to see is a kernel distance function between pairs of sample. Because it's a biased statistics for squared population of traditional MMD between the source and target samples. And K is positive semi-definite kernel function. So what is this correlation alignment? Correlation alignment aims to find a mapping from the representation of the source domain to the representation of the target domain by matching only the second-order statistics. In our framework, this would be equivalent to fixing our common representation matrices after normalizing them and then finding a weight matrix that aligns the two correlation matrices. Adapting a feature hierarchy to be domain invariant is more powerful than learning a mapping from the representation of one domain to those of another. Moreover, we use it as yet another similarity loss for our domain separation networks.